So, as I just mentioned, analytics is about counting, not queries. What kind of counting do you need to do? Well, we've already done one example, computing these likelihoods, a lot of counting to be done. We're going to talk about things like clustering. One example we already seen in the very first lecture, computing hash functions using locality-sensitive hashing is a kind of clustering. Data mining, finding bumps or statistically different regions in your data, finding rules, and learning latent features, which involves things like sampling from distributions, which are a guest lecture on Markov logic networks, that's MLNs we'll talk a little bit about. And we'll give one example using matrix multiplications also. But the bottom line that I want to talk about now, since we're going to cover some of these techniques only after unit 5 onwards, is that from the database perspective, all of these techniques require you to touch all your data. It's not about querying. If you're to touch all your data, then complex index structures for fast query processing, which traditional relational databases and data warehouse technologies like Teradata have, are pretty useless. So let me try to summarize the evolution of analytical databases and current trends. On the one hand, we have the NoSQL databases. So they got rid of ACID transactions, that is transaction isolation, to deal with conflicts and locking. None of that is there. They use, instead of having indexes, they essentially uses shards. That means distribution of data across different data nodes, distributed processing to rather than indexing. They don't have joins because joins are better done in, say, MapReduce, and they support columnar storage so that you can have wide data. And as we've just mentioned, big data is about wide data. On the other hand, there's another trend in the analytical database world, which is all about in-memory databases. So in-memory databases allow real-time transactions. They allow a variety of indexes and complex joins. The problem is that even as in-memory databases are great for very fast query processing and also large-scale transaction processing, it's back to the same problem of the number of possible options you can explore while doing slicing and dicing. You just can't do too much if your data is very wide. The second problem is that even in memory, the fact that you access data sequentially versus random access makes a huge difference given current memory hierarchies. And so in-memory databases are not really a panacea for large-scale data analytics today. When you have reasonable amount of data, it's still important to access your data sequentially, touch all of it to do analytical processing, and whether it's in memory or whether it's on disk, MapReduce is still a reasonably good paradigm that is an abstraction which allows you to touch all your data efficiently. So if I were to summarize the evolution of database technology, we started out with relational databases in a sort of one-size-fits-all. Whether you're doing transaction processing or you're doing reporting or even analytics, you can, from gigabytes of data, you can pretty much do one-size-fits-all using a relational database. Of course, whether you want to do OLAP or not will depend on the number of columns you have. If you have too many, then OLAP is kind of difficult to go through all the possibilities. But that's a combinatorial problem, not a database problem. Then, when we have large volumes, large number of columns, we went into column store data warehouses and terabytes of data. So the data warehouse technologies like Teradata, Oracle Data Warehouse, and stuff like that, they can deal with column stores and terabytes of data. And in parallel, we had distributed NoSQL row column stores, which essentially dealt with terabytes of data, but where you didn't really have to do joins. And when you wanted joins, you would do MapReduce, especially if you wanted to do joins for bulk analysis, and you could deal with tens of terabytes of data over there. In parallel, in-memory one-size-fits-all databases are also available, but they have their own challenges in terms of access patterns still mattering. And last but not least, Dremel, whereas now it's a one-size-fits-all database for petabytes of data, so you can still do bulk processing on it, but also you can do fast aggregation queries where only parts of the data are touched. In the last year, Cloudera, which is one of the Hadoop distributions, released a product called Impala, which is essentially an implementation of Dremel. It still has a long ways to go in terms of efficiency, but what it allows you to do is essentially do distributed query processing without having to do MapReduce. So it splits up your query, just like Dremel, into multiple subqueries, and each query can be executed on a separate data node. Data nodes can be in Hive, which is essentially HDFS plus some metadata, or they can be linked, as Hive also allows to link data to HBase. For those of you who want to learn more about Impala, Cloudera has enough documentation about it, plus of course it's freely downloadable as part of the distribution. Okay, so that brings us to the end of the section on load, 2 units on load. We started off talking about distributed files, which is the second basic element of big data after MapReduce. We talked about what databases are good for and why traditional databases were a happy compromise. And we covered the evolution of databases, the evolution of SQL, and the evolution of MapReduce itself. In the past few minutes, I've also tried to cover the big picture for database evolution as we see it today. And next week, we'll actually be having a guest lecture by Srikanta Betadur of IIIT Delhi on graph databases. We will not have separate quizzes and homeworks on the guest lecture, but you will have time to do homework 3 and the programming assignment that goes with it. We'll get started with unit 5, which is going to be on the subject learn, where we'll get started with unearthing facts from data using more complex classification, clustering, rule mining, all the things we just mentioned earlier in this summary.